So we're ready to continue our session. Our second speaker is Ewa Deelman, who is a research professor in the USC Computer Science Department and a research director at the USC Information Sciences Institute, or ISI. At ISI, Ewa leads the Pegasus project, which designs and implements workflow mapping techniques for large-scale applications running in distributed environments. Her research interests include the design and exploration of collaborative distributed scientific environments, with particular emphasis on workflow management, as well as the management of large amounts of data and metadata. Here to talk about the role of cyber infrastructure in science, presenting the challenges and opportunity, is Ewa Deelman.
Thank you so much, Valerie, for your kind introduction. Thank you. And I have to say, it's very hard to follow Ursula, who presented such beautiful simulations with cyber infrastructure, which people think of as plumbing. But hopefully, I'll make it a little bit more interesting. So today, I'd like to illustrate the impact of cyber infrastructure on modern science and make the case that cyber infrastructure is a connected system, and many of the scientific discoveries today were enabled by cyber infrastructure that has matured over the years. I believe that by connecting cyber infrastructure and computer science and multiple domains on science enhances our cyber infrastructure capabilities and also the capabilities that we deliver to science. I'll give some specific examples of applications that have benefited from complex CI over the years, and then I'll focus on the Pegasus workflow management system that has been developed in my group, and I'll describe some of the challenges that we faced in the various domains. So modern science today is really done across various scales. So you saw examples from Ursula. We also have an example which is at the very high end of the spectrum, the high energy physics collaboration that Atlas and CMS that discovered the Higgs boson in 2012. It took them 40 years from developing the hypothesis that such an elementary particle exists to the discovery of that particle. The instrument that they built at CERN cost over $5.5 billion to build. And if you look at the collaborations that worked on this project, there were over 6,000 people in Atlas and CMS that contributed to this discovery, and over 100 nations that participated in the LHC experiment. On the other end of the scale, you also have the same type of infrastructure that supports this large-scale science, also supports individual researchers. And this is an example of a graduate student, now a postdoc, Aria Gladstein, who did her PhD at University of Arizona. She used the power of the open science grid to trace the lineage of a population across time from Europe to the US. And she was asking questions: how did these people spread across the world? What demographic events occurred that made them move from one location to the next? So she used 40 different computational resources on the open science grid. She ran 12 million jobs to do her simulations, which all these jobs accumulated to about 1.5 million wall hours of computing. And with this technology, she was able to do things that previously were not possible. When I talk about cyber infrastructure, I've adopted the definition from Craig Stewart, which says that the cyber infrastructure consists of computing systems, data storage systems, advanced instruments and data repositories, visualization environments, and people, all linked together by software and high-performance networks to improve research productivity and enables breakthroughs not otherwise possible. In this talk, I really want to focus on this part of linked together. So connecting cyber infrastructure components, connecting people, and see how all these connections are made and how they can enable science in the various domains. People, as Ursula also mentioned, are at the heart of what's going on in cyber infrastructure and in science. And we see a variety of CI practitioners and facilitators that work with scientists and enable them to do the work. So on our campuses, we have people in research computing that work with the various faculty, enable them to do research on the campus resources. But we're also part of projects such as Exceed and the Campus Champions, where they enable these researchers to go from the local environment to the large resources and large national infrastructure. Obviously, the various infrastructure providers, such as the Open Science Grid and also various DOE laboratories, also have training and also support their users to work within these large infrastructures. And finally, there are also software institutes that are being funded by NSF to enable a community to get together and focus on improving an ecosystem within a particular area. So for example, the Science Gateways Community Institute is focusing on developing better cyber infrastructure for the gateways that many scientists use today. And another example is from high-energy physics, where they're also building a community resource for cyber infrastructure for that particular community. If you look at other enablers of modern science, one is clearly connecting to various data sources. So this is an example from University of California, San Diego, the WireFire platform. And this platform allows you to predict the spread of fire when wildfires occur in a particular area. So I went on to the website in late October when a Getty fire, so-called Getty fire, broke out in LA. And this platform automatically joins data from weather sources, weather stations, from weather predictions from the various cameras that are placed in the environment. And you see in these dark spots, the little dots, show you the possible spread of a wildfire. They also have a new technology that they recently incorporated, FIRIS, which is a fire-integrated system where planes fly over the fire and take pictures. These pictures have been reconstructed and contoured at UCSD to give you a better view of these fires. This is very useful, obviously, for emergency services, so firefighters and police, that determine the evacuation zones for this particular wildfire. And here, this was actually a very concrete example for me, because if you look at that red star on the map, this is where I live. And I was going down to work, which is south of this map, so I could either take the way by the ocean, which was in the just warning evacuation zone, or I could take the 405, which was closed at that time. And Ilka Tintas is going to give an invited talk in this room about this project on Thursday. Another enabler of modern science is connecting instruments and compute resources, and this is an example of a project that actually connects these things in a very remote environment in the South Pole. So IceCube is this huge neutrino detector. If you look at the graph on the left, this is a picture of the surface of the ice, of this octagonal shape where they have a little laboratory, which is the dark dot in the middle. This computational center takes data from all the sensors that are positioned within the ice. So the main laboratory is actually something you don't see. It's underneath the surface of the ice. It goes down about 2.5 kilometers. Within this ice are encased sensors, which they call digital optical modules, which detect the neutrinos as they pass through the ice. These sensors are suspended on cables that go up to the surface and send the information back to this computing center. There, the data is saved to disk, and all of it is shipped once a year to University of Wisconsin-Madison. Some of the data is also filtered in place to look for rare events or to send, which can alert other astrophysicists to events happening that they should target their telescopes to, for example. And this idea of creating triggers from instruments and alerting others of something interesting happening within the sky is very popular right now, and it's called the multi-messenger astrophysics. And you can argue whether this kickoff of that was in October of 2017. This was a time that LIGO and Virgo made the first detection of a gravitational wave that was produced by colliding neutron stars. So they have previously detected colliding black holes, but this was the first detection where other instruments, other telescopes could come in and look at that region of the sky and look for aftermath of this dynamic collision. So this is an application that's near and dear to my heart. I've been working with LIGO and partially with Virgo as well since 2001. On the left, you actually see a picture of me in 2001 at the Virgo Observatory. And in this project, we're connecting domain scientists of a gravitational wave physicist with computer scientists. And we're looking at enabling the science with computational technologies, with workflow management systems, where the scientists describe the computations as a complex workflow that can then be mapped onto the target resources. And if you can see, this collaboration takes time, and the first really significant result that we had in terms of science was in 2011, when a small group of LIGO scientists injected a fake signal into the data. And that signal was detected by the analysis that was developed by LIGO with the support of a Pegasus workflow management system. Unfortunately, this was a fake signal. At that time, LIGO was not sensitive enough to detect gravitational waves passing through it. However, this gave a confidence to the LIGO scientists that should a wave pass through the system, they would be able to detect it. And indeed, in 2015, when the advanced LIGO started, so when the new generation of instrument came on board, they were able to very quickly detect this gravitational wave. So they saw almost immediately the first blip. However, they didn't announce this detection until 6 months later. And I'll talk a little bit about why not, why it took such a long time to do this. And then in 2017, the multi-messenger neutron star merger occurred, and then also 3 of the LIGO founders received a Nobel Prize. So if we look a little bit into what happens behind these discoveries, these detections, so if we look at the 2015-2016 timeframe, in September 2015, LIGO detected a first signal that could have been a gravitational wave. In order to be certain that this was a gravitational wave and not a noise, they had to do a lot of analysis. And in this case, they ran 21,000 Pegasus workflows, and which constituted about 107 million tasks. So in this case, we connected the analysis that was designed by the LIGO scientists that measured the statistical significance of the signals with the efficient and scalable, robust execution of the tasks and data management across the systems, with the power of the cyberinfrastructure such as the LIGO clusters and also the EXCEED and NSF and NCSA's Blue Waters. If we look a little bit more deeper into what are the challenges of managing scientific workflows, such applications in these various environments, there are a number of challenges that are similar across domains. So we've been working with astronomers from IPAC and also with earthquake scientists from the Southern California Earthquake Center. And we discovered that all of them need a way to describe complex workflows in a simple way. And in some cases, people think of graphical interfaces to describe workflows. In our cases, because these workflows could have 600,000 nodes in them, we oftentimes look at to develop APIs or to the common languages that the scientists use in order to be able to describe their workflows. Then we also needed a process to distribute these computations onto the distributed resources. So scientists have access to a number of different systems, and it's important for them to be able to pick and choose which ones are appropriate for the work. And then we also need to deal with resources changing over time. So if you saw, LIGO has been operating since 2001. The resources that they have change constantly. So our focus and the solution that we came up to this problem was really to separate the workflow description, so what the scientist gives us, from the description of the execution environment. So then it is our job, the Pegasus jobs, to map these workflow descriptions onto the execution environment and to look at things like performance, scalability, reliability, so making sure that these large workflows execute efficiently. And we also provide monitoring tools so scientists can visualize the executions. And also we provide debugging tools so they can see what happens if we cannot recover from particular failures. So we're talking about these large workflows, but even looking at a particular, even one node workflow, what a scientist normally would have to do, for example, if they want to run Hello World at a resource at TAC, they would have to log in to the TAC resource. They would have to write a submit script to the particular batch system. They'll need to find the input data, stage it into this computational resource. They submit the script for execution. And then, hopefully, if everything goes well, they can stage out the analysis to the laptop or to other resources for visualization. However, what happens if a job crashed? How do you debug these? What if a Wrangler goes down or gets decommissioned, as often happens with these resources? What if you want to run across multiple platforms? So this is just an example of just one job running on a particular platform. Now imagine 600,000 of them and trying to manage them efficiently. So our approach is to basically connect the local environment that the users have to a more global environment where they're computing. So if we look at a typical environment where our scientists live, you have maybe a data source, so they have a sequencer in the lab. They have a local storage system where they collect the data from that instrument. They have an idea of how they want to describe the computations, and oftentimes, even though they're not using workflow management systems, they can graphically describe the various steps of what happens in the computations. And then finally, they have a local resource where they can do some of the computations, but that's usually not enough for them to do the full analysis. At the same time, they have access to various resources, so they have campus clusters. They have HPC resources, for example, at DOE labs or at Exceed. They have high throughput computing resources, so the resources, for example, of the Open Science Grid, and various clouds, both academic and industrial, such as AWS, or Chameleon on the academic side. So then it's our job to connect these resources for the scientists. So we place the workflow management system within that local resource, and we call it a submit node. We help the users describe the workflows in the way that Pegasus understands them as directed acyclic graphs. And then it's Pegasus' job to take these descriptions and map them onto the resources available to the users, to send work to these resources, and to send data and collect data after the execution. So you can imagine, for example, if you have a workflow that does an MPI computation followed by high throughput computing tasks during the post-processing, you would send the simulation to the HPC system once and the data that's needed for that. Then you would move the results to a high throughput computing resource to do post-processing, and then bring the results back if that's what the user wants, or just leave them there for further analysis. So if we look at the Pegasus workflow management system, it operates at the level of files in individual applications. So the node in the workflow are computations, and the data files flow through that. It allows scientists to describe the computational processes, the workflows at a logical level. So they can call a file f.a, but they don't specify a particular path for that file. That's resolved later. This way, we provide them portability of the workflow, so both the files and the application are described at a logical level, which is resolved. Then we also provide them with scalability, so we've run workflows with millions of tasks, terabytes of data within a particular workflow. We record everything that happens in the system so that the users can know exactly how the results were produced. And this also helps with reproducibility when somebody else wants to reproduce the results. And we include graphical monitoring debugging tools to enable users to figure out what's happening with the system. In terms of the workflow composition, we support a number of different APIs in Python. We have an integration with Jupyter Notebook. We have also APIs for R, Java, and Perl. And we also live within various user interfaces, in particular, most notably Hub 0, where the users don't even see us when they're using the system. If you look at the left, you see an abstract workflow. This is a Pegasus workflow that would have the nodes be the computations and the dependencies, show the data dependencies between them. These, as I mentioned before, are resource independent, so then the job of Pegasus is to take the abstract workflow and generate an executable workflow, where we already have then the different paths for the data that are resolved. We have the command lines for submission and the scripts for submission of the jobs to different resources. We also automatically add nodes, which you see in green, for data movement, so staging data in and out of the computations. So we know where we're going to execute the computations, or we know where we can retrieve the data. And then we also can register the data products after they're being generated, so others can use it as well, or just for the scientists to be able to keep track of what they've developed. And then finally, we also do a number of different optimizations. One of them is to clean up the workflow as we go along. So we remove the data that's no longer needed. And this is particularly important for large-scale applications that might be running in data-restricted environments. So that when you're running on an execution side that might not have as much storage as you need to be pretty efficient with it. So we support that case. Again, on the left here, you see this an executable workflow that's mapped to a single resource. If we map the abstract workflow to two different resources, which is seen, you can see in the middle, and if you focus on that orange rectangle, you can see that this part of the workflow looks a little bit different. Now we have green nodes added, so the data staging nodes are added to that workflow to move the data from the first resource to the next, and then to bring it back to join in with the rest of the workflow. Another example is running, again, same abstract workflow as you saw on the previous slide, but now running on an HPC resource. So imagine that the 4 nodes in the middle at the second level of jobs are high-throughput computing jobs, so single-core jobs, but you have a high-performance computing resource that's available to you. So Pegasus enables you to grab all these little jobs or high-throughput computing jobs together and manage them as one on an HPC system. So we have a specialized MPI engine that takes these jobs and run them in a master worker paradigm on the HPC system. To the HPC system, it looks like an MPI application, and for the user, you leverage the resources, high-performance computing resources, to do maybe thousands of these high-throughput computing jobs. So it's important also not only to compute, to connect to different heterogeneous resources, and this is an example from dark matter search, Xenon NT. They use resources of the Open Science Grid, but also the European grid infrastructure. But what's a little bit different in this case is they also need to connect to heterogeneous storage. So they use a specialized data management system, Rusio, and they use MongoDB for tracking of the data products, so when you register the data. So over the years, Pegasus has evolved to support a number of data transport systems and a number of different, what we call replica catalogs, so that we can enable scientists to deploy the system within the environment and use the types of resources that are already available to them. It's also important for us to not only connect efficiently to the resources, but connect to them at scale. So this is an example of an application from the Southern California Earthquake Center, the CyberShake application. So we've been working with them since 2003, and the scientists at SCEC wanted to develop physics-based shake maps of Southern California. And I know they hate when I say that because these are probabilistic seismic hazard maps, but shake maps make more sense to me. In any case, these are maps that they developed to determine what kind of shaking you can expect within a particular geographic region over the next 50 years. So that's the maximum peak acceleration that you can feel at a particular location. And this information is obviously very useful to building engineers when they are developing building codes for areas such as Southern California, which is very seismically active. Also for disaster planners, so when they're developing protections for the infrastructure, so the water and power, how to place them in a particular regions, how to protect them against earthquakes. And obviously insurance agencies that also make decisions about risk in various locations. So in 2018, 2019, normally, SCAC did a simulation of the peak acceleration in the Northern California area. Normally, they have focused on Southern California, but they've been able to have tuned the codes and to have access to the resources necessary to expand in the Northern California region. So now the map that you see here is a map of entire, most of the state of California, which is obviously a very seismically active area. In 2000, and the little white triangles, I don't know if they're very visible, but they represent the various workflows that were run to interpolate and create this map. In order to do the map of Northern California, they spent 180 million core hours. They ran almost 40,000 jobs. A lot of them are high-performance MPI codes that need to do the main simulations. They are often followed by high-throughput computing jobs. The data that flowed through these workflows amounted to 1.2 petabytes. 157 terabytes of that data was automatically transferred. So for example, when they're using NCSA Blue Waters and LSCF Titan, they were transferring data automatically with Pegasus between these resources. And in the end, they saved over 14 terabytes of data for the science. The total map, if you take the Southern California and Northern California, took 170 million core hours, which is over 19,000 years of computing. So as I alluded to a little bit, SCAC has very interesting workflows. They're a mix of MPI computation, large-scale simulations, and high-throughput computing. Over the years, we've done a number of different optimizations for SCAC. We look both from the point of view of the workflow of Pegasus, but SCAC also has evolved and has improved the applications to get us to this point. So in terms of Pegasus, we've done task clustering. So I mentioned it before, where you take high-throughput computing tasks and can place them in an MPI envelope and run them in a master-slave paradigm on an HPC system. On the other hand, SCAC also did a number of workflow restructuring. They tuned the MPI codes. They ported some of the codes to GPUs. So over the years, together, we were able to run on 9 different supercomputers. And now SCAC is making forays into Summit and Frontera as well to scale up the computations. If you look at, so in the case of SCAC, the resources are in some sense static. They send jobs to these large resources. However, when other applications may need these resources more on demand, especially when you have rare events that you're trying to track, as is the case with CASA, the Collaborative Adaptive Sensing of Atmosphere application, which is led out of UMass Amherst. And this work of connecting workflow management systems with resource provisioning systems is done under the umbrella of a Dynamo project led out of Renzi. And the issue is that this collaboration, CASA, has 7 weather radars, near-Earth radars in the Dallas-Fort Worth area. Most of the time when they're doing prediction, the nowcast of what's going to happen in the next 30 minutes, or if they're looking at the maximum wind velocities in a particular area, they don't need much computing. The weather is clear, the computations go fairly quickly. However, if you have severe events, tornadoes, hails, then the complexity of these computations increases. So they need to dynamically acquire resources in order to be able to support the nowcasts and the wind velocity predictions. So they reach out to systems that allow them to provision these on demand. And we've been working with them to connect to various resources, those for example, of Exogeny and Chameleon, which is an academic cloud, and connect to them via high-performance networks so that we can move the data that's being collected by the radars in Dallas, or in Dallas-Fort Worth area, where the nowcasts are being needed, to the computational and storage resources that can do the simulations fast enough to be able to be useful. And obviously, Dallas-Fort Worth is a very populated area, so providing accurate and fast nowcast of what's happening when you have severe weather in a particular region is very important. Another area where we see these connections of where we connect cyber infrastructures is connecting computer science research with the development that we do. So in our case, we structured the workflows as directed acyclic graphs. And from that, we're able to gain all the benefits of reusing the various graph traversal algorithms, node clustering, pruning, and other complex graph transformations in our work. We also use hierarchical structures and recursion to achieve scalability and dynamic behavior of our workflows. Then we also develop new algorithms to look at issues of task clustering, data placement. So if you have data-intensive jobs, we want to place the tasks where the data sources are. Data reuse, in some cases, the data already is pre-computed, so somebody else maybe ran the computation, or the workload ran up to a certain point, so you can reuse this data. In other cases, we need to estimate the resource usage, like the case in CASA. We need to know how many resources we want to provision for this, from the environment to support the computations. And recently also we are looking at issues of in situ workflows. So workflows where you have an analysis following a simulation. So you have a large-scale simulation running in an HPC system, and you want to analyze in time what's happening and potentially steer that simulation. So this is a work led by Michaela Taufer out of University of Tennessee, Knoxville, and other collaborators at Cornell and University of New Mexico. We also benefited over the years to connect our cyber infrastructure to what's already out there and is very robust. So since 2001, we've been leveraging HT Condor's capabilities to do remote job submission to these heterogeneous and distributed resources. They help us manage also the dependencies expressed in the DAGs. And they also provide low-level job retries and error recovery. So that when we in our environment on the submit host, so that local resource to the particular scientist, we place the Pegasus system and also some specific components from HT Condor. And from there, we can spread out to the remote execution environment. And being able to connect these components already together so we don't have to manage the low-level details, we're able to focus on other aspects of scientific workflow management. So we looked at issues of planning and replanning in case of failures, automating the data management on behalf of the users, providing various user-friendly monitoring and debugging tools, and also the specialized MPI engines that I described. We also provide provenance tracking. And recently, we also have two projects that have focused on data integrity. Especially in distributed environments, this is something that you have to be very conscious of, that data has not been changed from the time that you deposit it in storage to the time you're using it in a workflow. So two projects that one was led by Indiana University and the second one out of Renzi, SWIP and ARIS, are looking at these issues and developing the workflows, adding new capabilities to Pegasus to check the checksums as the data is being ingested by the system. Another important connection that we need to make in the CI world is between computer science research and domain applications. So over the years, since about 2002, we've been working with astronomers from Caltech, IPAC, and their application Montage. This is a very interesting application. It generates scientific-grade mosaics of the sky. And it's an important application for computer science and cyber infrastructure. And I'm sure some of you have used it already to test your algorithms, the scalability or efficiency of your algorithms under various conditions. Montage is great because it's an open source code. You have access to the data. It's open data as well. It's astronomy data. It's scalable and robust, so you can scale it up and down depending on what type of testing you're doing. And this is one of the workflows that we use every day excuse me, in our builds and tests to make sure that our software works correctly. And others have used it successfully to do workflow scheduling, resource provisioning, and provenance tracking. An important part also of this connection is to working with a number of different applications. So in the Southern California Earthquake Center, I already mentioned, on the bottom you see of this graph that shows the timelines of releases of Pegasus. You see the various SCEG-driven improvements that we've done to the software. On the top, you see the improvements that we've done based on the LIGO needs. And the LIGO needs were such that they oftentimes focus on data efficiency, so efficient use of storage where they're executing. And most of the workflows were high throughput computing workflows. So and really the two didn't really come together. The needs of these two didn't come together till 2015, when LIGO suddenly went from the clusters within the collaboration, which were high throughput computing clusters, to high performance computing resources. And there they started using the task clustering and the MPI workflow engine and other solutions that we developed for SCEC to make use of these high performance computing environments for their workloads. Another issue that's very important when you're talking about scalability, so I mentioned Montage as an application that we can use to test our software, but we also need infrastructures to do the testing. And I was very happy to see that recently NSF has funded the Fabric project led by Ilya Baldin out of Renzi. So this project will build a national scale computer science research testbed where they are connecting to the existing infrastructure that we have in wireless and clouds and national facilities. So you can do various types of experiments in IoT, network protocols, distributed systems, and workflows. So this is, I'm looking very much forward to using this for our work, and also to developing applications that can, more than just Montage, that can really help us test the various software pieces. So another part of what we want to do in improving the connectivity of cyber infrastructure, not only the testing and developing benchmarks, but also improving the connectivity of the various systems that are being built. Sometimes these systems are being built in isolation, so we want to connect these systems together and to connect the people that develop CI. Recently, in order to do that, my collaborators from University of Utah, Notre Dame, and Renzi have come together, and we are piloting a project to develop a plan and a model for a cyber infrastructure center of excellence. We just started our second year of a project, and this is a center dedicated to enhancing CI for science, and particularly looking at the NSF large facilities. We want to provide a platform for knowledge sharing and community building and forum discussion around CI sustainability and workforce development. We are currently fostering various working groups, so discussions around the science data lifecycle, identity management, and others. And we're also partnering with other efforts, so Trusted CI, the Open Science Grid, to start these discussions around cyber infrastructure. At the same time, as we increase the connectivity of CI, we also may increase its complexity. So the more things you connect together, the more powerful you make your systems, the more complex they become. And so you need more automation to make these systems work for the users. And you also need more autonomy, because you cannot have something overarching, really controlling everything to every detail. So you need the various pieces of cyber infrastructure to become more autonomous. So there is a good role for machine learning, and we see it already in anomaly detection for scientific workflows and many other areas of cyber infrastructure where machine learning can help. However, it can also pose challenges or make the challenges that we have today even worse. So how do we provide tools for scientists to be able to look at the results and trust them? So how do we know that what we're generating is actually true? How do we allow scientists to inspect the results, to look at the level of detail that they need to make sure that the calculations are correct? How do we help them understand what the cyber infrastructure has done for them? And finally, how do you allow other scientists to reproduce what a particular scientist is seeing? I believe also the automation, just like it did in industry when the cars came online and factories, automation also will change the workforce landscape. And I'm very curious to know how the scientists, how we will look in the future. What will be our role? How are we going to convey our ideas to the system? So what our interfaces will be to the new systems that are coming online. How this infrastructure will mature to be something that's just like an easy button or something that can read your intentions. So with that thought, I would like to give big thanks to my Pegasus team that's done an awesome job over the years, and to many of the amazing collaborators that I had the privileges to work with. Thank you.
And we have time for just a few questions, if you want to go to the microphone. Okay. And we'll start with microphone 5.
Hi, I'm Marta. I have a question about Pegasus workflows. Can you somehow optimize the workflow execution? I mean, can you select appropriate number of computational resources for each job in the workflow?
Yes, so we have some capabilities embedded in the workflow system to do that, but we also have interfaces where you can plug your own scheduling algorithms to look at whichever way you want to schedule particular resources. So you can, for example, either for data selection or for resource selection, you can program Pegasus to follow whatever algorithm you want to put in.
Okay, thank you.
Ursa.
Yes.
Can you optimize the workflow to make sacrifices? For example, let's say you want to be fast, but you can't be fast if you do all your jobs properly. So for instance, for fast response, when you have a gravitational wave, you might want to not be too accurate in favor of being quick. So can the workflow make that choice?
Yes, so I think, so we do provide various domain-specific interfaces. In this case, the way we could program this is to give the opportunity to not only select the resources, but select the models, the applications that you're going to run, because I believe that's what you're alluding to. So if you have a time crunch, just use some other, change the parameters for a simulation, or maybe choose a model that's more emulative than a detailed simulation. So I believe we can do that, and I would love to work with examples such as those. Thank you.
Okay. And I think we have another question at microphone 2.
Yes. So your slides mentioned a number of HPC institutions with successful Pegasus collaborations. I'd like to hear information about the unique challenges of operating Pegasus at those places.
Yes, so there are a number of challenges. Obviously, what we need is a way, because we assume that the user comes from the outside, we need a way for the users to be able, of a system to be able to submit jobs to a particular resource. So we're using, for example, pieces of a HD Condor, that very small pieces that can be put on the remote end. SCEC has done a number of solutions where you can also have a small job that calls back home, and you can use what we call glidance to come into the HPC system, and then you place the jobs into that resource. OLCF has various ways of working within the Kubernetes infrastructure to run on resources such as Summit. So every system is, individual in some way. It used to be that you had well-defined interfaces like Globus Gram, if it existed on a resource and exists at NERSC, for example, we use that. So we'd prefer to have actually the connectors to the various HPC resources to make it easier for us to work with them. But that has been a challenge over the years, and I'm hoping that at some point it will get better, but it hasn't. And nowadays you also have two-factor authentication, which makes everything more difficult.
And due to time, so I want to thank Ewa again, and I also want to present a gift. So first, let's thank Ewa. Okay. And then I would like to present a gift.
Oh, very kind of you.
Yes, on behalf of the General Chair, so Michaela Topher, to say thank you very much. We enjoyed hearing about Cyberinfrastructure.
Thank
so
you very
again,
much.
thank you to Ewa.
An invite and a gift. Thank you.